So my iPad is not somehow. Can you hear me now?
Yes, sir.
Okay. Why is the iPad not showing? Okay, let me stop sharing and start sharing again. Okay, can you see the screen now?
Sir.
Okay, I hope you can see the screen now. Can someone confirm?
Yes, sir. Yes, sir.
Okay, cool. Thank you. So let's start. And so last time we looked at the caching problem and we saw an greedy algorithm for that. So today we'll be looking at one or maybe two, depending on the time, graph problems. And the most like basic graph problem is of shortest paths. Okay. So what is the input? Input is a graph G. And there is some weight function, let's say. It's set to, let's say, positive reals or non-negative reals. And a source S. Okay. And what is the output that you want? The output you want is shortest paths. Okay, so instead of W, let's call it L because the book uses L. Okay, so shortest paths from S to all the vertices in G. Okay, so this is the problem. So what is the shortest path? So length of path, let's say L of P is equal to summation of E belongs to P, L of E. Okay, so you just sum them up, all of them, all the edges in the path, and then that gives you the length of the path. Okay. Okay. Good. So now the question is that how do we compute the shortest path from S to all the vertices in G? Okay. So the algorithm which we are going to look at is just, it will keep, so this is Dijkstra's algorithm. Okay. So what does it do? So it starts with S. Okay. It always maintains a set S. Initially S is equal to just S. So it starts with S, and then, so current set whatever is S, and then it looks for the cheapest, like, so it also looks for, it calculates this function. So that U is in S, and then D of U plus L of UV. Okay. So, or L of E, L of UV, because we want to specify, like, instead of just writing E and L and E, my L and E look quite similar. Okay, so what are we trying to do here? We are trying to compute the shortest path. So initially, when, just hold on for a moment. Yeah. So, yeah, what I was saying is that how do we compute this? We compute this function. So we always, for every vertex in S, so let's say every vertex V in S, we also store this value of dV. So whatever vertices are in S, for them we have already computed the shortest path. So that is going to be our invariant. So dV is going to be the shortest path. Okay. So for vertices in S, we have already computed shortest paths. So initially, what should we put the value of D of S, let's say?
0.
0, right? So that will be the starting point. Okay. Then we find the vertex that minimizes this quantity at every stage. Okay. And then what we do, we add that vertex to S. Sorry. Can you hear me now?
Yes, sir.
Yeah. I think I went off for a second, but hopefully I'm audible. Okay. So, and then we add that word V to S, putting the D of V is equal to this D prime function that we have mentioned here. Okay. So what happens? We first find a vertex which is basically closest to S, because right now S is just the smallest. Then we update the D value of this vertex. Then we find something else and so on. So okay, let's first write the algorithm formally, and then we'll look at the next one. Okay. So first step is let. Okay. Set of explored nodes, and for each U in S, we store the distance D of U always. Okay. As I said, initially what do we have? So these are like kind of invariants. They are not really doing anything. That is just for saying what it is. Initially s is equal to s and d of s is equal to 0, as I said. And while s is not all of v, that is, we have found out the shortest path to all the vertices, select the node v that is not in s, that also with at least one edge, right? One edge of the form uv. So also we are doing this one thing that we are looking at. So let's say that we are doing it for directed graphs. Just for simplicity, and if we can solve this problem for directed graphs, then we can solve for undirected also. How? Can someone tell? Suppose we solve the shortest path problem for directed graphs. That in a directed graph we can find out the minimum distance from S to every other vertex. Then I claim that we can solve it in undirected graphs also. So how can that be done?
We can make for an undirected graph. We can make make two copies of every edge going in the opposite directions with the same weight.
Exactly. So if you have this edge UV with weight LE, okay, then what you do? You take U2V and both of them. So this is E1, this is E2, L of E1 using bracket, L of E1. See, my L and D's are quite similar. L of E2. Okay, so but if you get confused, please let me know. Okay, is equal to L of E. So we will be looking for directed things. Okay. All right. So I was describing the algorithm. So what did I say? Select the node V in S, V not in S, such that there is at least one edge of the form UV where U is in S. That minimizes the function d prime of V is equal to minimum of E is equal to UV. U belongs to U plus L of E, and yeah, that minimizes this quantity. Okay, and then what did we say? Add, sorry, this should be within the for loop, while loop. Add V to S, set dV is equal to d prime V, and semicolons, and while. Okay. Is it clear? Any questions about the algorithm? So what are we saying basically? That okay, we have S, this set S, and now we want to add another vertex to the set S, and for S we have already computed the shortest path. So the only way to reach any vertex outside S is that you reach some vertexes in S and then there is an edge. So this is V, this is U. So this is not really an edge, this is like a path. So maybe you went somewhere, then you went to U, and this is the shortest path to U. But then from U you went to V, and now this V is the one which is the shortest path from S that has not yet been added. Okay, so in a way, how does it look like that? You start with the source, and then there is this circle or sphere, whatever, that you grow slowly. And whatever vertex comes first, you know, that you add. Then this sphere grows again, and then whatever vertex come, then it gets added. Vertices get added in the order of distance from S. Okay, so you are growing this sphere. So this is like a BFS in some sense, but this BFS is not depending on the length of the path. I mean, not length as in not length of the path in number of edges, but this BFS actually depends on the weighted length of the path. So you grow this like like a ripple, it just grows, and as it expands, whatever vertices start coming in, they start getting added to S. Okay. So is the algorithm clear? Or if it is not clear, is there any question about the algorithm till now? Okay, you might have seen this algorithm. This is a very basic graph algorithm in like data structure and algorithm course also. Okay, so now let's quickly. Okay, so suppose let's take an example also just for the same example in the book. But so you have this S, then you have U, V, you have X, you have Y, you have Z. You have this is 1, this is 2, this is 4, 3, 1, 3. Okay. So now what will get added in the first run of the algorithm if this is the graph? What is S initially? S is just this. So what will get added in the first run? Capital S.
U.
Yes. In the first run, U gets added because what is the vertex that minimizes this quantity? D prime U is equal to minimum of E is equal to UV, U belongs to S. So right now this U is only S, right? So E has to have one endpoint as S. So now there are these three edges that get considered, and out of which one minimizes? So this initially is 0 because this is D of S, which is 0, and now plus the length of E. So now length of E is 1, 4, and 2, and D of S is 0, so 1 is minimum. So this U gets added. So first S grows like this in the first step. Okay. In the second step, what gets added? What gets added in the second step?
V or X.
V or X, yeah. So now there is a tie that both of these, because this is at distance, so this is D of U is now 1. Okay, so now from D of U plus L of E, if we do for X, that gets us 2, and D of S plus L of E for this edge, if we do, then we get D prime of V is equal to 2, and D prime of X is equal to 2. Okay, so let's say we add V for now. Then in the third step, now these edges will also be considered, but their value is going to be harder because now D of V is equal to 2. V has been added. So now D prime of X via this edge will be 4. D prime of Z via this edge will be 5, and so on. So now what will be added? x will be added, right? Because x has still 2. So now, okay, so not this, I mean like this. Close like this. Now it will include x also. Okay. And then what will be d of x? Will be 2, right? Because from this path. Now what will get added? After this, y will get added because d prime of y via this edge is going to be 3, and d prime of z will be 4. 4 via this edge and 5 via this edge. So we put d of y is equal to 3. So y will get added. D of y is equal to 3, and finally z will get added by putting d of z is equal to 4 via this path. Okay. So there is another thing, that the way we were storing only the distances in the dv, but we can also store the paths implicitly. So how to store the paths? Suppose the algorithm, like not only someone is not only asking for the distance from S to the shortest distance from S to the vertices, but also wants the paths, that if you are given some vertex, then you can also tell the path. So how do you do that? Have you seen
We can,
that? Or yeah,
for each vertex, we can make an array of parents. So for each vertex, we can find the parent in the shortest path.
exactly. So make an array of parents of vertices in the shortest path. So whenever this dv is getting set, you look for with what edge it has been set, right? So here dy has been set by this edge. So what we'll put in p of y is equal to x, parent of y. Okay. Similarly, when dx was being put to, what we'll be putting the parent of x? This, because of this edge dx was put to, right? So p of x is u, right? Similarly, p of v is equal to s itself. P of u is also equal to s, and here p of z is equal to x, right? So now suppose we want to find the shortest path to z. So okay, we look at p of z is equal to x. All right. So we go to x. So we put z as the last vertex, or we can later reverse the string. I'm reversing the string right now itself. So z, then we put x, then we go to x. What is the parent of x? It is u. So you put u, then you go to u. What is the parent of u? It is s. So you can get this. All right. So this does not take any extra time. Just while you are updating the, we'll come to the time, but just while you are updating the distance, you can also update the parent, and you can find out the path. Okay. Any questions about this? So let's quickly prove the correctness of the algorithm. So how can we prove the correctness? So let's show the lemma for every v in v, d of s, d of v is correctly set by the algorithm when v is added to s. Okay, this is what we want to show. So how can we show that?
So if we like inductively assume that for all the nodes in set S, they have been assigned correct distance. So
Exactly.
the node which minimizes d dash v will have to be minimum because all other paths would be of greater length for v. because like
Yeah.
any other path would involve some node which is not present in S and it already has a greater distance.
For that. Good. So exactly what Shravan says. So he's proving by induction. So he says that we can assume that all the vertices which are added in S have the correct path, and why we can assume that, because we will go by induction. So proof by induction, let's say on size of S. Size of S, the way it grows by the algorithm. Okay, so base case is mod S is equal to 1, that is S is equal to S, and then like we have put D of S equal to 0, which is correct. And let's now look at the induction step. So what do we want in induction step? That suppose mod S is equal to K, and for all the vertices in S, D of S, vertices V in S, D of V is correct. That is the length of shortest path. Good. So now suppose the new vertex being added is V. Okay, so what do we know? That V minimizes this quantity. Right? And this quantity we call whatever D prime. Let's call it. Okay. Good. So this is the quantity that V minimizes. So suppose that this did not happen, that we are adding the shortest distance of V. Okay. So then what has to happen in that case? So suppose, so you have this S. Suppose our S was this right now. Let's use a different color. This is our current S. This is the V that we are adding. So we have, let's say, this U, because of which this was happening, and this is now a path, like, many vertices can be here. So this is D of U, right? And this is L of UV, right? Good. So suppose what we stored for D is not the shortest path. That means there is some shortest path. So let P prime be the shortest path. So suppose, like, suppose DUV is not, or D of V is not length of shortest path. Okay, so let P prime be the shortest path. So now this P prime has to, it does not go via U, so it goes via something else, or even via U, it doesn't matter. So it goes, but it has to cross, P prime has to get out of S, right? Because V is outside S, and small s is inside S, right? So P prime has to get out of S. Okay. So let the last vertex in S of P prime be U prime, and the first vertex outside be V prime. Okay. So what can happen? Maybe P prime goes somewhere some vertex u prime here, and then it steps out to v prime, and then it goes to v somehow. Okay. So, I mean, again, these paths are, we should use dots ideally because we don't know how many edges. Okay. Good. So this is how the paths are. So now what we know is that v prime v. So basically what we want the contradiction now that, okay, so if this is the shortest path, that means its length is less than d of u plus this L of uv that we got, because this is, if this is not the shortest path, if this is not the shortest path, then that means this total path length, has to be smaller than this yellow thing. That means, of course, this path length is smaller than the yellow thing. Then why are we not adding v prime and adding? Okay, that is the idea, that if this whole purple thing, or this green thing, is shorter than the yellow thing, then why are we not adding a subpath of that? Instead of v, why are we not adding v prime? So that is what our proof is going to be. Okay. All right. So let d star be, or let d star is equal to d of v, right? The distance that we have stored. So we know that d prime of v is equal to d star, or d star is equal to d prime of v, because v was the one minimizing this quantity d prime of v, which is equal to, now this path length, so call this path PSU, call this path PSU prime, this one, okay, and then from, let's call this path something else. Okay, so if we need it, we'll call it. Okay, so L of, so what is this d prime v? D prime is v is by definition length of this path, which is d of u. Okay, let's call it d of u plus length of uv, right, by definition. And what is d of u? Okay, so, and now this thing, definitely, since we know that this is not the shortest path, by definition of shortest path, this has to be strictly less than d of u prime plus length of this path. So let's call this p double prime. Length of p double prime, which is from u prime to v, let's say. Okay, and which is definitely less than or equal to d of u prime plus length of, now this whole path length is at most this edge, this one edge that is there, that is u prime v prime. So that means that d prime v, what is this quantity? This is d prime of v prime. So what we've got is that d prime v is strictly less than d prime of v prime. Then why did we choose? This is a contradiction to the choice of v. Okay. So is the proof clear? So again, like, don't get lost in symbols and so on. As I said, that since v is being added, if this is not the shortest path to v, then there has to be some other path, and that some other path has to cross s. So look at the first vertex where it crossed s. Since the whole path is shorter, This is the vertex that will minimize and not V. Okay. Any question about this? All right. If not, then we'll go into the running time analysis. Okay. So now for running time analysis, if you implement it naively, then every stage a vertex being added. So order n times, or exactly n minus 1 times in fact. The while loop runs. And now inside the while loop, every time, for every vertex that is outside, you are looking at the neighbors and so on. All the edges that are there, all the e's that are there. So every while loop, let's say m comparisons to find which v to be added. So total we get order mn. But this is like, we can improve this. But for that, we need a data structure, okay? And the data structure is priority queue. So you must have seen it, I think, but if you have not, then if you must have seen heaps, and priority queue can be very easily implemented using heaps. So you can just go to the section 2.5 of the book, and there they give it in detail. I'll just mention the operations that are going to be supported. So just like heap, this priority queue will be able to do certain operations. Okay. So what are the operations? So first is going to be start heap, and it will take a number n. It will returns an empty heap. Empty heap h that can store n elements. Okay, and how much time does it take? It takes order n time to set. Second operation that we need is insert h comma v. Okay, insert item v into h. Okay, so we insert item v into the heap, and this takes time order log n. If n is the current size. Okay. Now the third operation that the heap supports is find min. So again, what are we trying to do here is just maintaining this data structure where for each element there is a value, right? And that is what, so find min is, so there is a key for each element in the heap, and then we want to perform certain operations on the heap. Like we want to find the minimum, we want to maybe delete something, maybe we want to add something, and so on in the heap. So for that, we are these are the things. So finds minimum, does not delete, and all these can be supported. So this is a priority queue because it is implemented using a heap, so it has slightly more operations than the heap. So now we have this find min. Find min can be done in order 1 time because this is basically the root of the heap. But if we want to suppose delete something, So then we need to first find it and then delete it. So delete I from the heap. This will take order n time, order log n time, because the heap is like, sort of balanced binary tree. So you first need to find it and delete it, right? And then there is this operation called extract min, which finds and deletes, or outputs the min and deletes it. So this is a combination of find, min, and delete. So this takes order log n time. And then there are two more operations actually, which is just, so now this is just, so as I said, this is implemented, this priority queue is implemented in a heap. So in the heap, actually you have heap as an array, which has n elements. And then the heap will have these things. So you can also store the position. Suppose you have a graph and you want to have for each vertex, you want to store some information, some key in the heap, and that is what you want to, like, order the heap by whatever key. Okay, then you might want to access the key immediately, that given a vertex, maybe we want to access the key. So for that we can maintain another array, which is position of v. So what will, so if suppose the key of some vertex v is at 15th position here, then here at vth position we'll store 15. So suppose we want to now just find out the key of some vertex v, then we go to this, go like, okay, this is at the 15th position in the array of the heap, and then we directly go to the 15th position to find out the key of v. So this is like a pointer array which stores the position of v. So using this we can implement another operation, which is, let's say, delete h comma position of v. So, and we were deleting a particular key from h. So I is a key.
Sir, how does delete h comma I take order log n time? Won't we have to search for the key in order n time? Because it is not sorted in any meaningful
No.
order, right?
No, it is order. It is. So if you know the heap, then like it's yeah, there is some meaningful order. So you can actually do that in a heap. It's not completely like random.
Yes, sir, I know that, but I don't think that it is possible to find the key in order n time, order log n time, because like the heap only has a property that the two children will be greater than or less than the parent, right? So you'll have to go through every element in order to find that key, because you can't branch out into any fashion. You can't say that only, you can't say like in binary search tree you can say that only left child will have, only right child will have, but in this case you can't say anything.
Mhm. Okay, so just hold on. Maybe I'm missing something, but I'm not sure.
Sir, in the book actually it is written that I is the position, like the index in the.
Oh,
Like,
yes, you are right. I is the position. Yes, 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 yes. You are right. You're right. So delete. Yep, yep, yep. Thank you. Thank you for pointing out. Delete. Yeah, v is the value or v is the key. So we can the value. So insert item v, or with value v, and delete the item at position I. Thank you. Yeah. yeah, we cannot search so fast in the heap. Thank you for pointing out. Good. So yeah, we can go and search, basically look at the item at position I and delete it, but deleting it might create some gap or in the heap, and then we need to like reposition things and apply the heapify up or heapify down and so on. So that will take log and time. Good. So now we have delete this position of V, that again can be done in log and time, and this position of V we can find out using this array that we maintain. So this is log and time, and then we have, what else do we have? Another operation. Another operation is change key. So again H V alpha, and now we again, so we go for V's. We can find first the position of V using this array, and then we go there and see, okay, what is stored at that position, and we can change it to alpha. Basically here we don't need to look at what it is. So this is changes the key of V to alpha. So again, it goes here, looks at, okay, which position the key of V is, goes there and changes this key to alpha. Okay. And again, since this change of key might make the heap order bad, this will also take log n time. So these are the operations that a priority queue supports, and as I said, you can go and have a look. So yeah, I was yeah, here I should have said that position I instead of element I, and that's all. These are the operations. So using these operations, now we want to do a faster implementation of Dijkstra's. So how do we do that? Any ideas?
We can use the priority queue to find out the next vertex which should be added using the key as the shortest path, shortest length path to that vertex.
Yeah, not exactly the shortest path, because we don't know the shortest path, and that's what we want to. Yeah, but this, like, whatever we have computed till now, that kind of shortest path. So this d prime value we can use as the key. Okay, so what do? We want to maintain this d prime value for every vertex that is outside S. Right? So now at every moment we have this S, and we have initially that can be, so initially it's easy to see because you have just S, and what is this d prime value for everything else is whatever, infinite or something, and only for neighbors of S this d prime will be finite, right? Okay, good. But now let's look at one particular instance of the algorithm where the V is being added to S and there's some W that is not being added to S. So since we are storing this d prime V value for everybody, we can extract min in order log n time. Sorry, right? So, but now we need to update for other vertices which are in S. How to update? this extract min, and we want to do it as fast as possible. So how will we do that? Any idea? So the thing is that this W, it has already some d prime value if it is not, infinite or whatever. So if this W does not have an edge from V, if this edge, if VW does not exist, then can it change the d prime value of W? It remains the same, right? Because whatever vertices were there as because of that, whatever value W got or didn't get, that will not change because V does not have an edge to W anyway, right? So then d prime W remains the same. So all that we need to do is update d prime W for vertices that are neighbors of V, right? So now each vertex is getting added and each time its neighbors are being accessed. Vertex is getting added, its neighbors are being accessed, right? And so on. So how many times this update operation is happening? How many times?
The degree.
Yeah, for one vertex. So dv times when v is added to s. So total every vertex gets added once, right, to s. So how many times this happens now? What is the summation of degrees?
M.
M.
Yeah, number of edges, right? So total m times. So what is the total? So and this update, what is this update? This update will be done using the change key operation. So this change key operation happens m times and it takes order log n time. So total time taken is order m log n by this change key operation, right? Similarly, the extract min operation happens n times, right? So the total time taken by the extract min operation is order n log n, and setup and all takes order m time, let's say. So total time is order m log n. Okay. Why does the setup take order m time? Because you have to look at all the edges to see that okay whether the d prime is, no, actually you don't have to look at all the edges for setting up d prime, but yeah, maybe order n time. But anyway, this is the highest time which is taken by the change key operation, and that is order m time, order m log n time, right? Actually, even so, set not the setup, but you will be doing this order m time anyway. So setup will take maybe order n time because initially you want to set up this array, the position of V array, and you need to set up the heap itself, which will take n time. So maybe setup will take order n time, but total time is order m log n because of this operation. So any questions about this? About the implementation of Dijkstra's for minimum span entry? So if not, then we can stop here today because I don't want to start another topic. And in the next lecture on Thursday, we'll look at the minimum spanning tree problem. Still, like, if you want to ask any question about today's thing, you can ask. So this is a very classic algorithm, and yeah, the implementation is the main thing where, like, you must have seen the implementation also maybe. So this can be implemented in order m log n. So if there are no questions, then thank you for coming. And see you guys on Thursday. Thank you.